Welcome back to the Math Professors. If you enjoy content that can be found in a college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover linear independence today. So the set of vectors S, which is v1, v2, all the way to vn, in vector space V, is said to be linearly independent when the vector equation c1v1 plus c2v2 all the way up to cnvn equals a zero vector has only the trivial solution. So this just means that c1 has to equal c2, which has to equal c3, all the way up to cn. They all have to be zero simultaneously. Otherwise, we'd say the vectors are linearly dependent. So what I want to do is I want to determine if the set of vectors is linearly independent or linearly dependent. So let's just say linearly independent. Otherwise, they'll be dependent. So I want to explain really what this means, and these two vectors will give us some kind of geometric kind of idea of what it means to be linearly independent. So linear independent basically means that the vectors themselves, each vector in this set is going to go in a unique direction. And I picked two vectors here that don't go in a unique direction. So what I have is I have vector 2, -1. So over 2, down 1, it's going to give us, I think it's going to do it in green. So this is this first vector. That would be our v1. And then the next vector is going to be -4, 2. So I'm going to have to go over 4 and then up 2. And what we're going to get is we're going to get this vector. Now these two vectors are not linearly independent because they don't technically go in unique directions. Like I could build v2 just by multiplying v1 by a constant. So in this case, really just multiplying v1 by -2. So v2 can be built from the previous vector. So really what I'm saying is that for these things to be linearly independent, each one of the vectors have to go in a unique direction. Otherwise, one of the vectors can be written as a linear combination of the remaining vectors. Or this, vector here can be written as, linear combination of, the one remaining vector. And then we'll do it with three vectors and show you linear independence and linear dependence and explain how one vector can be written from, say, the other two if it's linearly dependent. Otherwise, they will all be going in unique directions if they're independent. So let's prove that this works. So what I have to do is I have to set up this linear combination of these two vectors. So I have to test this equation, c1v1 plus c2v2 is equal to the zero vector. Now these are R2 vectors, so the zero vector in R2 is going to be 0, 0. So this is going to be c1 times the first vector plus c2 times the second vector is going to be equal to the zero vector. Now we've already kind of practiced this, that this is going to give us this equation, the previous one that I'll do the work this time, and then from now on we'll just write our matrix and then row reduce. So distributing the constants through. Now adding vectors says I have to add their corresponding components. So this is 2c1 minus 4c2, and that's going to be the first component, and then the second is going to be minus 1c1 plus 2c2. And this has to be equal to 0, 0. Now for two vectors to be equal, that means the first component of this has to equal the first component of that of each side. So that means 2c1 minus 4c2 would have to be equal to 0. And then similarly for the second component. So minus 1c1 plus 2c2 would also have to be equal to 0. And we can write this in augmented matrix form, so then we can row reduce. So this could be 2 minus 4, 0. This could be minus 1. This could be 2. This could be 0. And there's a bunch of different ways we can row reduce. You can have your calculator do this, or we can do this, by hand. So I would go ahead and maybe clear out row 1. So what I could do is, actually the way I do this by hand is I'd interchange the rows first. So switch row 1 with row 2. So minus 2, boom, and then this is going to be 2 minus 4, 0. We'll do this with the calculator next. Now what I can do is, so this was, just row 1 switched with row 2. Now I can clear out that second row. So 2 row 1 plus row 2 is going to be my new row 2. And this is going to give us minus 1, 2, 0. And these will all zero out. Now, when we row reduce, we usually like to make this a 1, so this is going to be minus row 1 is my new row 1. So finally get this equation, 1 minus 2, 0, and then 0, 0, 0. Now, what does this say? Well, the first line says 1c1 minus 2c2 is equal to 0. And the other line says 0 is equal to 0, so there's no real information. So what I can do is I can solve this for c1. So c1 is equal to 2c2. Now I write the right-hand side as a parameter, so I say let c2 equal t. So then finally we would have c1 is equal to 2t, and then c2 would just be equal to t. What I'm trying to show is if this thing is linearly independent or this is linearly dependent. And for it to be linearly independent, the only solution would have to be zeros. Now clearly, like if c1 and c2 are equal to 0, the entire left-hand side is going to be 0, and that will equal the right-hand side will be equal to 0. So the trivial solution is always going to work. I just want to see if there's a non-trivial solution. So, if I plug in t equals 0, of course this will be 0, this will be 0. We already know that works. But what if I let t equals 1? Have I found a solution to where it's not the trivial solution? So let's let, t equal 1. So then c1 would be equal to 2, and c2 would be equal to 1. So I can rewrite this equation right here. So let's rewrite this equation. So c1 is going to be 2 times 2 comma negative 1 plus 1 times minus 4 comma 2 is equal to 0 comma 0. And what this actually shows me is I can actually write the second vector as a multiple of the first vector. I can just solve for this vector. Remember what that is this is just, this is 2v1 plus, v2 is equal to the 0 vector. So I could solve this for v2, and doing that I can say that v2 is nothing more than negative 2v1, which is what we've already said. That this is just this matrix multiplied by negative 2. I'm going to say this vector multiplied by negative 2. Showing that this is linearly dependent. I can write one vector as a linear combination of the remaining. Alright, let's show one that is linearly independent. So I want to determine if this set of vectors, this v1, v2, v3, is linearly independent or linearly dependent. And we know that we have to set up this vector equation. So, c1, v1 plus c2, v2 plus c3, v3 being equal to the 0 vector, and these are our 3 vectors, so the 0 vector being 0, 0, 0. So that's really just setting up, this equation right here. I just want to know if there's a solution besides the trivial. Of course, c1, c2, c3 equals 0 is going to make this thing 0, but are there other ones that work? Well, we've already done the work to show you that I can write this in augmented matrix form. The first column is going to be the first vector, second column is the second vector, third column is the third vector, and the last column is going to be the equals. And when I solve this, when I row reduce echelon form this thing, so this is going to be an RREF. You're welcome to do that in your calculator, or do it by hand. Or just showing you how to do it. So we're going to row reduce echelon form, this matrix A, and what we're going to get back is the identity, joined with 0. So what we're going to get is 1, 0, 0, 0, 1, 0, 0, 0, 1, and these will be zeros. And what this says is the top line says, 1c1 plus 0c2 plus 0c3 is equal to 0, or, just c1 is equal to 0. Very similar, the second line says c2 is equal to 0, and then the third line says c3 is equal to 0. Verifying that the only solutions here are just 0, 0, 0. So we'd say that this is these vectors, or this set S, is linearly independent. Let's do another set. Let's say this is A. Let's do B. What if I say S is equal to, let's just do 2 vectors, because it doesn't really matter. It doesn't have to be 3 components for these things, but let's say 0, 1, 5. Okay. Now, 2 3-dimensional vectors, can be still linearly independent, but we would still kind of plug in, in this to this vector equation and see if this works. And I wanted to put 0 in here because this is it's an example that always shows up. So what we know is this is just going to be C1V1 plus C2V2 would be equal to the next the 0 vector in R3. And setting this up, we're going to have this would be equal to 0, 0, 0. This is 4, negative 1, 5, and this will be equal to 0, 0, 0. Now, C1 column, C2 column, equal column. And now when I row reduce echelon form this thing, well, what would happen is we're going to get C2 is going to have to be equal to 0. So when you row reduce echelon form, you're going to have something that looks like this. It's super easy to do. I could interchange rows, or I can just make this a 1 by multiplying that by negative 1, so 0, 1, 0. And then I can use this to clear out the other rows. So what you're going to see here is you're going to see something that row reduces to look like this, and then the rest will be equal to 0. Now what this top line says is, this says 0C1 plus 1C2 is equal to 0, which really just says that C2 is equal to 0. And the other lines say that 0 is equal to 0. So there's no information from these, all you just get is true statements. So, well, what does that say? Remember, for this thing to be linearly independent, it says that all your coefficients, all your scalar coefficients have to be equal to 0, but it only guarantees that C2 has to be equal to 0. What about C1? Well, let's take a look. If C2 is equal to 0, well, 0 times this thing will clearly be 0. But what can C1 be? Because it didn't give any stipulations on C1. It allows C1 to be free. C1 looks like it can be any number is what we're saying, because it didn't, it didn't restrict it. And is that true? Well, what if C1 is 5? Well, 5 times 0, comma 0, comma 0, 5 times the 0 vector is just going to be, the 0 vector. So it wouldn't matter if this is 5 or 6 or 7 or 8 or pi. It wouldn't really matter. That any number times a 0 vector is going to give a 0. So the only thing that's forced to be 0 for this to be true is this thing to be equal to 0. So since C2 has to be 0 and C1 can be any number, well, it doesn't satisfy that. They both have to be equal to 0. So we'd say that this is linearly dependent. So let's determine if this set is linearly independent or linearly dependent. So we know we're going to have to set up the equation C1V1 plus C2V2 plus C3V3 is equal to the 0 vector. So C1 times the first vector, C2 times the second, plus C3 times the third is equal to the 0 vector in R3. Okay, so we know when we set this up, we're going to get this augmented matrix. And then 0, 0, 0. And what I'm going to do is I'm going to row reduce echelon form this. And we're going to get 1, 0, negative 1, 0. This is going to be 0, 1, 2, 0. And then finally we're going to have a 0 row on the bottom. Okay, boom. So what does this say? Well, this says, the top line says C1 minus C3 is equal to 0. The second line says that C2 plus 2C3 is equal to 0. So we will solve these for, well, since they both share C3, let's make those the independent variable. So then C1 is going to equal C3, and then C2 is going to be minus 2C3. So we can let C3 equal T. So we can parameterize this. So then I have C1 is equal to C3, which is T. C2 is equal to minus C3, which is T. And then finally, C3 is equal to T. Now, again, we know that if I plug in T equals 0, this is 0, this is 0, this is 0, still sum to be the 0 vector. That's always going to work. I want to know if there are other numbers. And I don't know, let's choose T equals 1. It doesn't really matter. You can choose T equals 3 or T equals 5. I'm just trying to show you that there are other C values besides C1 equals 0, C2 equals 0, C3 equals 0, because this is linearly dependent. So if you actually get some fractions here, if everything is divisible by 2, I'd pick T equals 2. I might make it easy. So I'm going to let T equals 1. So then C1 would be 1, C2 is going to be negative 2, and C3 would be equal to 1. So we already proved that, we already know that this means that this is linearly, dependent. And again, what does that mean? Well, that means that one of the vectors can be written as a linear combination of the other two vectors, or really, like, one of them doesn't really give us any new direction, essentially. So I'm just going to show that. So this is enough to prove that it's linearly dependent. But what that means is that C1, which is just 1, so I can say 1 times this 1, 2, 3, minus 2 times the 0, 1, 2, plus 1 times negative 1, 0, 1 is equal to, 0, comma, 0, comma, 0. Or I can say, just V1 minus 2V2 plus V3 is equal to the 0 vector. And I can solve this out. Let's just solve it for V1 because it's easy. So I can basically say V1 can be built from the other two vectors. So, adding 2V2, subtracting V3. So we know that this vector could be built by 2 of these minus 1 of these. So really, I don't need that third vector. It's not helpful when I'm trying to create a new direction. So that's why this is linearly dependent. Now we can do other tests for independence and dependence, and our subspaces don't always have to be the Euclidean spaces like R. What if I want to test like P2, for instance? Does that change very much? So let's do 2 more examples. One using maybe P2 and one maybe using M2 comma 2, just to show you that all this stuff still works, and it's very similar setups. All right, so I want to know if this set is linearly independent or linearly dependent again. So still the same thing. So what I'm going to do is, this is the first vector, second vector, third vector. So I'd have C1 times 1 plus x minus 2x squared plus C2 times 2 plus 5x minus x squared plus C3, and this is 0 plus 1x plus x squared. Just making sure that I write all the constants. And then, the 0 vector for P2, which is polynomials of degree 2 or less, is 0 plus 0x plus 0x squared. What's interesting is once you send everything through combined like terms, that this acts very much like your Euclidean space. So this is C1 plus C1x minus 2C1x squared plus 2C2 plus 5C2x minus C2x squared plus 0C3 plus 1C3x plus C3x squared, and this has to be equal to, again, 0 plus 0x plus 0x squared. And then we're going to combine our like terms. So, what are our constants? Well, C1 plus 2C2 plus 0C3 plus. Now, the parentheses are just for flair, okay, just to show you where they're coming from. Now, for the x's, I'm going to have C1, for this is plus 5C2, and then for this it's going to be plus 1C3. Now, the parentheses matter because they're all going to be x's. I just pulled them out. And then similarly for the quadratics, I have minus 2C1 minus C2 plus C3, and all of those are x squareds, and 0 plus 0x plus 0x squared. Okay, so what are we trying to really show here is when are these things equal? When polynomials are equal, the constant will be equal to 0, the linear term will be equal to 0, and also the quadratic term will be equal to 0. Or it just gives us a system of equations that says C1 plus 2C2 plus 0C3 is equal to 0. The next says C1 plus 5C2 plus 1C3 is equal to 0. And finally the last, 2C1 minus C2 plus C3 is equal to 0. And I could really just, again, write this in augmented form to where, this is 1, 1, minus 2, which again just comes from the coefficients of, the first vector. The next column is going to be 2, 5, negative 1, again, coefficients of this vector. And then finally the coefficients of this vector would be, 0, 1, 1. And then this is going to be the coefficients here, which would be 0, 0, 0. So again, it acts just like R2. Very, very similar. Now, when we row reduce echelon form this, what we're going to get is 1, 2, 0, 0. This would be 0, 1, 1/3, 0, and this would be 0, 0, 0, 0. Again, essentially, immediately almost showing linear independence. I can see that this is going to give us a non-trivial solution. Or I can say that this says the top line says C1 plus 2C2 is equal to 0. The bottom line says C2 plus 1/3 C3 is equal to 0. So then solving for, I guess it doesn't really matter in this case. I'm going to solve the first one for, it would make more sense to solve it for C2. Doesn't matter. It doesn't matter. So, yeah, well, I'll solve the first one for C2, and then I'll also solve C3 for C2. So, let's do it this way. What I notice is they share a C2 in the equation. So if I solve this top one for C1, we're going to have 2C2. And what I can do is I can solve this for C3. So let's multiply everything by 3. So 3C2 plus C3 is equal to 0. And then I can solve this for C3. So it says that C3 is equal to minus 3C2. All right. Now, since there's only a C2, I can let T equal C2. So then finally, C1 is equal to 2T. C2 is equal to T. And then C3 is equal to minus 3T. Again, showing that there's other solutions besides, 0, 0, 0. Again, if T is equal to 0, of course it's going to work. But I'll let T equal 1 again. So then what I'd have is C1 equal 2, C2 equal 1, and then C3 equal to negative 3. So again, non-trivial solution. This is linearly dependent. Which basically says I can write one of these vectors in terms of the other two, and when you plug them in, it'd probably be easier to isolate, the second one. So I can say, 2 times the first one plus 1 times the second vector, minus 3 times the third vector is equal to the 0 vector. Or I can isolate this, that, this is V2. So I can say that, this is 1V2 minus 3V3. This is 2V1 is equal to, the 0 vector. So I can say that V2 can be built from negative 2 of the first plus 3 of the last vectors. So this center vector would be minus 2 times this plus 3 times this. So it can be built from, one of the vectors can be built from the other two. I chose to solve for V2 because it's the one that had a coefficient of 1. I just went after the easy one. Last example, just to show you different. So for the last example, is this linearly independent or linearly dependent? So let's set up the equation. C1v1 plus C2v2 plus C3v3, because there's only 3 vectors, being equal to the 0 vector. So C1 times the first vector. Remember, these are in M2 by 2 matrices, so they're matrices that are 2 by 2. So plus 2 C2 times the next vector plus C3 times the last vector would have to be equal to the 0 vector, and the 0 vector in that vector space is that. Okay. And I'm going to show you algebraically that it really turns into something that's very similar to R4. So distributing the roots, 2C1, 1C1, 0C1, 1C1, plus 3C2, 0C2, 2C2, 1C2, plus 1C3, 0C3, 2C3, 0C3 is equal to, this 0 vector. Now, adding these things together just means I have to add their corresponding entries. So the top left, or row 1, column 1, row 1, column 2, row 2, column 2, and then finally the bottom right one would be 1C1 plus 1C2 plus 0C3, again is equal to, this is 0 vector. And what we get here is a system of equations. I have 4 equations. The first equation says, well, these are equal, and the top lefts are equal. So this is 2c1 plus 3c2 plus 1c3 is equal to 0. Next is going to be, let's do this one, 1c1 plus 0c2 plus 0c3 is equal to 0. And then the bottom left is 0c1 plus 2c2 plus 2c3 is equal to 0. And finally the last one, 1c1 plus 1c2 plus 0c3 is equal to 0. And when I write this in augmented matrix form so I can row reduce to solve, 2, 1, 0, 1. What you notice is 2, 1, 0, 1. The first column really just corresponds to the coefficients in front of this first vector. The next one's going to be 3, 0, 2, 1, just because I've written them in that way as far as the system. 2, 1. And then finally 1, 0, 2, 0. And it's got to be equal to this, 0, 0, 0, 0. Now, when we row reduce echelon form this, it's going to give us our C values. Of course, just having 3 of them, it's going to give us 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So what's nice is the last row zeroes out, which is okay. Just because the last row zeroes out doesn't guarantee that this is, infinite solutions or dependence, because remember, the first line says C1 equals 0. That's all that says, C1 plus 0c2 plus 0c3 is equal to 0. The next one says c2 is equal to 0. Next one says c3 is equal to 0. Guaranteeing that only the trivial solution works. So these things are linearly independent. If you like the stuff, please subscribe.